Hello everyone, this is going to be section 10.3 class problems. So first, for each of the following situations, we're going to determine whether we have a graph, a tree, forest, or neither of those. So first, we have a connected graph that has 8 vertices and 7 edges. So this is, of course, going to be a tree, and it's going to follow the rule of tree that is essentially you need to have for the number of edges n-1 vertices. So given that the vertices are 8, then the edges are going to be 7, and we can have a tree via the tree characterization theorem. Now, for a connected graph with 6 vertices and 6 edges, it's going to be a different situation. Notice that it's not going to be a tree immediately by the same characterization theorem. And just because we're assuming that it's going to be connected, then it means that we're going to contain at least one circuit. And if it contains at least one circuit, then that means that it cannot be, it's not a tree, it's not a forest either. So the answer will be neither. Another situation will be with C, where we have a graph with 9 vertices and 8 edges, and it has 2 connected components. So since it has 2 connected components, it has exactly n minus k, which will be 9 minus the number of components, which is k, 7. It should have 7 edges, okay? And because we have 8 edges, this will be for trees, right? If trees, it will have 7 edges, but because we have 8 edges, which is bigger than 7, then it means that one of the components has a circuit. So it cannot be classified as a tree, it cannot be classified as a forest. So the answer will be neither. Now for D, we have a graph with 5 vertices, 5 edges, and no isolated vertices. So in this case, it's not going to be a tree because we know that for being a tree, we will need only 4 edges, and we have 5. So with 5 edges, we have a surplus edge. If it's connected, then it will have a circuit. If it's disconnected, at least one of the components has a circuit. So either way, it's not going to be circuit free. So it cannot be a forest either. And in this case, we have a situation where we can classify this as neither as well. All right, so now for question number 2, we have the n-1 edge theorem to use and the full binary tree formulas to answer the following questions. So first, a tree has 15 vertices. How many edges does it have? Well, because in this one we already know it's a tree, so we know that the number of edges is going to be 15 minus 1, so it's going to have 14 edges. Now similarly in B, if a tree has 20 edges, so we know that the number of edges is going to be n-1, so we want to know how many vertices it's going to have. So because the tree has 20 edges, then we know that n, which is going to be the number of vertices, is going to be 21. Now, a full binary tree is going to have 10 internal vertices. So how many leaves and total vertices does it have? And so the full binary tree, and I'm going to call it FBT, implies that the number of leaves is going to be I plus 1, where I is the number of internal vertices. The number of your internal vertex. So in this case, because we have 10 internal vertex, then we're going to have 11 leaves. Okay? Now the total number of vertices is going to be, of course, given by the number I of internal vertices plus the number L of leaves And so in this case, it will be 10 plus 11 will be 21. And so that will be the total number of vertices that this binary tree has. Now, on question D, we want to know what is the minimum height of a binary tree that has 50 leaves. So remember that a binary tree has a height, a minimum height, or height 8, has as has at most 2 to the h leaves. So we need that 2 to the h is bigger than 50, since that's going to be the number of leaves that we know that we have. So in this case, notice that 2 to the 5 is 32, which is less than 50, right? But we need bigger than that. So 2 to the 6 now is 64, and that is bigger than 50. So that's going to be the answer here. So the minimum height would be, if we find out here, so the log base 2 of 50 is another way of doing this. And we'll look for the ceiling of this, which is going to give us 6. So that's going to give us the number of exponent here. That's also another way that we can find this. So the minimum length will be 6. All right, so now for question number 3, we're considering the rooted tree below. So we have that the root here is A, and we want to consider a couple of questions about this tree. So first, we want to consider what is the level of each of the vertices. So of course, because A is the root, then A is at level 0. Then we have B and D that are at level 1. C as well is at level 1. So B is level 1, C is level 1, D is level 1. Now, E, F, G, H, and I, those are all level 2. And finally, J and K will be level 3. So let's write that out. So E, F, G, H, and I are going to be level 2, and J and K are level 3. So now also, what is the height of the tree? Well, the height of the tree is the max level that is achieved. So in this case, we noted that the maximum level that we achieve is 3. And so that's going to be the height. Now, if we're listing all the leaves is everything that is not going to be a bird, or we're going to consider this like vertex with no children. So we can consider F, G, H, I, J, and K. So each of these vertex that they're not going to have any more children. Now we can list the childrens of B, and so if we list the childrens of B is everything that is below B. So the childrens of B will be E and F. So those are the immediate nodes after this. And we think about the parent of G, then obviously that's going to be what comes above of G, which is going to be the node C. Now, let's talk about possible siblings in this tree. So let's name 2 pair of siblings. So for example, B, C, D would be a pair of siblings, since they're at the same level. But you can also go with like J and K, since they're also at the same level. So that's one way of putting it. Now we can talk about, is this a binary tree, a full binary tree? And so it's not a binary tree because the vertex A has 3 children. The binary tree can only have 2 children. So not binary. More than 2 children. So really we can think of this as like a tree area or ternary tree, more likely. And so since it's not binary at all, the concept of full binary isn't really going to apply. Now let's talk a little bit about traversals. So for question 4, we want to perform traversals on the binary tree below and write a sequence that we'll use for each of them. So first, we're going to go with the preorder, which is the node, the root node, the left, and then the right. And so of course, because we're starting from the node, then we go with 1 is first, then we'll go to 2, and then we'll go to 4, and then to 5. Notice that this is always go from the root node to the next root node, and then it goes to the leaves. Then we'll transition to the right, which will be the 3, 6, 7. Now, in order, the leaves node and the root, we also can consider, here we go first, but the left side, we go with the 4, then we transition to 2, and then we transition to 5. Since we're going to the left, the node, and the right in here, and then we'll transition then to 1, and then we'll transition here to 6, 3, and 7 on the right side. Now for the post order, which is the opposite, we'll go with left, right, and node, then we'll go like 4, 5, 2, since we're going first 4, then 5, then 2. Then now we're going in the other direction, 6, 7, 3, and then finally 1. Okay, so that's the way of traversal and the tree orders that we can consider here. All right, so now for question number 5, we're considering the expression x plus y times c minus w. We can write this as a tree. This expression, we can draw this the binary expression tree for this mathematical expression. So we will start with the center. So we'll start with the times, and that will be the root node here. Then we'll go to the operation on this side, which will be the plus, and then we'll have the operation here would be the minus. And then of course, then the childrens are going to be x here and y. And in here are going to be c and w. Now, like using the tree, we're going to write all the possible traversals. So first, we're going to use the prefix, the Polish notation, which is equivalent to the order that we described before, to the NLR notation. So in this one, we'll start with the main operation, which is the times. Then we go with the plus. Then we have the leaves on the left side, which is x and y. Then we go with the minus, which will be the operation on the right side, and then CW. If instead we use the infix notation, which is equivalent to the LNR traversal, then we're going with first being x, then the operation, which is the plus, then the y, then the root node, which is the x, then we go with the c, and then the minus, which is the operation between this and the w. And then finally for the postfix notation, the RPN, which is equivalent to the LRN, then we have the first, we go with the leaves, so we have x, y, then we have the operations in the middle, plus, then we go with the next set of leaves, which is c and w, the operation that they're using, and finally the root node, which is the times. Now for internal vertices, notice that we have the internal vertices being x, or times, plus, and minus, so this is 3 internal vertex. And the leaves are going to be, of course, x, y, c, and w, which are the things that are being operated. This is a full binary tree. Notice that every time there's a division in two, every internal vertex has exactly 2 childrens, so it's going to match the definition on the formula of the binary tree. We have the leaves being I plus 1, which in this case is going to mean that the 4 leaves are equivalent to the 3 internal vertices plus 1. Okay, so see you in part 2.